So I've got this motor with a resolver, and I have a Copley drive that can do clock and data. All Copley drives that can do clock and data can connect to the Copley serial resolver adapter, and the adapter converts the resolver, excites the resolver, does the sine cosine, and then just converts it to clock and data and transmits it like a normal serial encoder to any of the drives that are capable to do, let's say, a BIS-C or an SSI, but just basic clock and data. So the CSR is a little tiny, inch by half an inch by almost 2 inches adapter. And inside this adapter, this connector going in, a connector going out, you've got this little chip here that fits in there. It's the world's smallest serial adapter board for the modules, right? So the panels might use this because it's easier to cable to, and then the modules, you can integrate this onto your board and adapt to resolvers. So small form factor, easy integration, high speed. Now, we used to say greater than 10,000 RPM, but we just tested it to 30,000 RPM with a 4-pole motor. So I'm going to spin it at 15,000. Don't try this at home because we don't want to fling your magnets off. High resolution, 16 bits of effective resolution. That's not necessarily accuracy, but if you have 2 A to D's reading sine to cosine, that improves the bit resolution. So 65536, sort of, 2 to the 16. And also you can have multi-speed, like 2 resolver cycles for 1 rev. But if you have the normal 1 resolver cycle for 1 rev, that's like a single turn absolute encoder. So you just turn the power on and you know where you are within 1 absolute rev of the encoder. Of course, we can emulate output and do a burst mode to the 0 or the north marker. The inputs, of course, are resolver, motor temperature sensor, Hall pass-through, and a shield. That's good to have a shield pass-through. Yep, clock and data, motor temperature feeds through. We also have cables to adapt. One end goes to the motor and the other end goes to the drive for like the XTL Zenus, the XSJ Zenus. The ADP, the ACJ is coming out with this clock and data. The ruggedized drives and all the plus drives, of course, that can do clock and data. Might not have a cable for everything, but for the most part, there's several options for cables. So let's just kind of go through the techie stuff. CSR mod is just this little board here. And there's the specky stuff, normal resolver, hot, cold, kind of ruggedized kind of design. So you got your basic resolver. We're going to excite it and read the sine cosine. And you got a nice shield going to earth and an inner twist. If you have inner shields, outer shield and inner shield, the inner shield goes to the signal ground. This thing gets its power, of course, from the drive. So there's a drive which is powering it, and we're taking the clock and data. This is for the plus drive. There would be data on S and S naught instead of A and A naught. This is the Zenus XTL, the standard Zenus drive. And so there's a pass through, and you could, maybe some sort of feedback faults detected. You can issue a fault in the drive. And there's another cable that goes between the adapter and the motor, of course. The board is small and fits into tight spaces. Again, world's smallest resolver to serial adapter. This is how you'd wire it up in your module application. But the basic pin out here is one side goes to the drive, DRV, another side goes to the motor. And we pass excite the resolver and pass it off to the drive. So these cable assemblies, we make, there's a connector kit, of course, so you don't need to buy cables from us. But sometimes when you're doing a retrofit, going from an old obsolete 8367 DSP to a new ARM drive, you might want to get these cable assemblies. Gosh, they're awfully well documented here. And that's how it fits together. That's pretty cool. And there's an ordering guide for the cables. I got an XTL, I want the cable that goes from the drive to the CSR, I get this one. I want the one that goes from the CSR to the motor, I get that one. Or I get a connector kit and I order the CSR. So that's what you order. And we'll just take a look here. So this is the little CSR. So I got one cable going to the drive. This is the new ARM that takes clock and data. And this would adapt to the old drive's cable. So I have an old 8367 Rev 0 drive and a Rev 2 over here. And I have an Infinor motor. We'll take a quick peek at the wiring up. So I got the tag data. I found it on the web. I put the data in. So this thing on 200 volts should be able to go 20,000 RPM. I've only got 120 volts AC rectified. So if you had 240 volts rectified, of course you could hit the 30,000. Don't go over 30,000 because there is a limit. You know, it's the max speed. I had this cable to an XPC. I could have just bought those adapters and plugged in a different drive with it, but I moved the wires over to the old XTL just so I can demonstrate how easy it is to go from the old drive to the new drive with the CSR. So let's do that. So I've got this system up and running, and it's got certain settings and characteristics. So we'll take a look at it. Brushless rotary resolver 16384. I could put 65536 in there, but that was the value that was defaulted. If you had a break and emulate out, there's even a burst mode to go to the 0 marker. And then the data for the motor gets input. You see here 30,000 RPM. That's crazy. Calculate initial tuning parameters based on the good data. And in the past, maybe somebody tuned it. Look, nice round numbers. So we'll just see what the bandwidth is. So the bandwidth should be about a kilohertz if somebody tuned it properly. Yeah, about a kilohertz there. Auto tuning calculated. They should all end up at a kilohertz. And the peak and continuous current here. That's a 40 amp drive, by the way. I don't know what it's doing driving a 4 amp motor, but you know, people think they need more peak. And then there's the tuning for the velocity loop, a velocity limit set, an output filter. This one had 400 hertz single pole low pass. And the P loop, basically minimal load. If you had a huge inertia, you want to cut the PP down, maybe allow some air while you're moving. Nice tracking window for move and settle. And we'll take a look at what does it look like for a move. All right, that was 16,000 RPM, no error, no voltage limit warning, plenty of the bus is drooping down a little bit, but there's the current, so like half an amp, a little bit, you know, plus or minus. And then if we zoom in on the following error in blue, and you can see it's like plus or minus, 25, less than 25 counts while we're moving. I mean, that's literally a phase lock on position over time, or that's a pretty darn good velocity. Throw a strobe on that thing, and you'll see it's just drifting plus or minus a few counts, right? So what we're going to do to get from one drive to the next is we save a CCX file. So this is an old CCX file for this motor, HGHI Infinor. So I've already saved it, but I'll save it again. Yeah, I'll overwrite that. So it was working. I saved the file. Now I'm going to connect to the other drive here and do the same thing. We'll just load the file into the new drive. Take the old file, right? And we'll just load it into the new drive. We should check the tuning, you know, check the bandwidth and maybe check the velocity loop tuning. But if all things are the same, this CME version 8.1, I'm using beta 24, is pretty friendly. And now I'm going to reconnect to the new drive. And I don't know what's in there, but let's file, restore, CCX file, and let's find it here. GHI Infinor So open the file. Okay. Yeah, it's a resolver, and go to CSR. Yeah, go ahead. I got the CSR. And then save the flash, right? It's in RAM. Now it's in flash. And everything should be exactly the same. Let's just do a little peek here. Oh, that's something's new, like multi-speed. That's a new feature for the plus drive. Pretty cool. Yeah, emulated out, max frequencies for burst mode. Lots of cool stuff. New features, right? You got more filters. Anyways, the motor data is the same, and the I loop is the same. We'll check the bandwidth, right? Like, you got a new drive, load the old file. The current loop bandwidth should also be about a kilohertz, plus or minus 100 hertz. So yeah, there we go. So that's good. We can characterize the velocity loop, but I'm just going to skip right to making a big move here and change the time to 5 seconds. Fingers crossed on autonomy. Goes. All right. Reading trace data from Amplifier. Okay, so I was close to the limit. I'm bumping my head a little bit on the voltage limit. So yeah, maybe I need to turn the gain down a little bit. That will affect my following error here. The current looks very similar, plus or minus half an amp, maybe a little bit more. I got a little bit more ripple on this, but still, plus or minus less than 25 counts there. So maybe we should go back and do a little tuning. I'm just gonna knock that integrator down a little bit, and let's leave that alone. Let's change the trajectory, knock a little bit off of there. Okay, 15,000 RPM, not bad for half voltage. And yeah, there we go. So a little less bumping our head into there. Yeah, it still looks like about plus or minus 10 or 20 counts. So very similar. The current loop on average is about a half an amp. There's a little bit more noise apparent because of the new drive has more sampling points. So it's just more samples, that's all. So you can see the 4 millisecond sample rate is like 10 times more samples than the old drive. So the new drive is better, right? Just keep saying that. The new drive is better. 400 hertz Butterworth. You can do all kinds of crazy filters, 32-bit floating point instead of 16-bit integral. And the only difference, was a little different tuning of the velocity loop, seemed to improve performance. I just turned the integrator down a little bit, less integrator wind up. Got to watch that VP, and otherwise this looks pretty good. There was one application that was pure velocity. In the past, we didn't use an integrator. We had to turn the VP down a little bit. I just added a little bit of velocity current feed forward. This is a new feature. So you got some friction when you're going fast or some viscosity. You can compensate for it with a feed forward and bring that velocity tracking right, just like plus or minus a few counts while you're moving. Of course, this is position mode, so there's no error in velocity over time because you're plus or minus a few counts over time. So the strobe will not drift on this one. But pure velocity, you're either above or below. Try to get right on the line, and you can do that with some feed forward turn. We ended up turning the integrator off on that one. But anyways, that's it for migrating from an old 8367 obsolete DSP to a new ARM processor, same drive, same hardware, same features, just more new features like BIS-C or serial adapter. You can stock one drive instead of two drives. This can now adapt to, and the cost is pretty small for this. The resolver drive used to cost more, so you'll save money, right? We like to save money. And thanks for watching.